So we're a minute and a quarter early, that's excellent. Okay, my name's Anthony. I'm also known as AJ. I'm also known as the Debian guy, but currently I work for Red Hat. So, okay, that wasn't meant to be a joke, but I do. I'm a release engineer in the Brisbane office for Red Hat. We maintain the build environment and actually pushing stuff out. Okay, so this talks about debugging a system problem that we had. Our build environment was crashing every few days, and that it took us a couple of months to actually work out what exactly the problem was and how to actually get it fixed. So this is a bit of a walkthrough of that, and hopefully gives you some ideas on how to deal with similar out-of-memory issues and general strategies of debugging this sort of problem. Okay, so Koji is the build system used in Fedora and internally in Red Hat. It's an open source project. It was originally developed inside Red Hat and then brought into Fedora. A few other people are running it on systems. There was a talk at the Brisbane conference by Dennis Gilmore about how it works. It's set up so that basically it's got a database store for all the metadata about the builds and how they relate to particular releases and the history of everything. It has a hub server which does XML-RPC, which accepts XML-RPC queries and lets clients access the database indirectly. It has a web service, so users can go and see what builds have happened and where all the logs are up to and whatever else. And it has a bunch of workers which actually do the builds, so they're running mock and RPM build. Okay, so memory usage is an important thing, which I guess everyone here knows. One question, how many people here are sysadmins? How many people here are developers? Okay, excellent. So I'm a developer more than a sysadmin. I do run my own systems, but I prefer to have systems run for me so that someone else can worry about that. I'm currently using like 2 laptops and a Shiva plug and a NAS box at home. So that's my sysadmin stuff these days, and I think it's great. But when you're dealing with apps, then they need to run in memory. You can have plenty of swap, but if you don't have enough memory, it won't work very well because the CPU has to execute from memory. You can have all sorts of ways of allocating stuff like that these days. The swap, there is mmap, so that you can treat a file on disk as though it's in memory without it actually having to be in memory constantly. And you can have files on NFS rather than disk. You can do whatever, but ultimately it needs to get into memory. Once you've got too much stuff in memory, you'll get the killer happening. How many people have actually been killed? Excellent. So the killer is Linux's way of saying, okay, there's too much crap running, I need to get rid of some stuff so I can do anything at all, and I'll choose Apache, bye. It's got actually these days a fairly good way of working out which process to kill. It'll kill the ones with lots of memory, with lots of recent allocations. So back in the 2.4, 2.2 days, it was terrible. These days, I actually find it pretty good, and I'm starting to think about running without swap, so that rather than when I run out of memory, I get complete lag because I'm going into swap all the time, it'll just start killing the process and I won't have to worry about it. I haven't actually been game to try that except on my laptop, and it worked okay on my laptop, but I've got swap enabled at the minute, so. Okay, so the problem we had was in August, September, the Koji hub would just get out of memory and start crashing. So it'd lag as it was going into swap. The killer would start up, Nagios reports would happen, the sysadmins would log in, see that there are messages in the log and reboot the server, and then it was all okay again. Now, that's kind of fine. Like, the sysadmins get an address report, they log in, see what's going on. 5 minutes later, the server's rebooted. Because it's only running Apache stuff and all the database stuff is elsewhere, all the files are on NFS, so there's no need for a long FS check. It's all straight back up in 5-10 minutes. There's no data loss. All the actual builds are running on other machines that aren't crashing, so they're just continuing. There is a restart needed because the XML RPC calls are over TCP and there's a single authenticated connection, so that's a bit of a pain. But no data loss, 10 minutes kind of downtime for the web interface, and you're all back up. So it kind of works that way. And the reason it kind of works is the design. So you've got a separate database that stays up. PostgreSQL is working nice and reliably. You've got a separate NFS server. That works fine. And your Apache process, if it all gets killed and restarted, it doesn't actually lose any information. And the workers are all independent as well, so you're not actually losing the builds. But it doesn't work completely. For one thing, because the workers, you need to log into them and do a CoGD restart. And for the other thing is, I imagine most of the sysadmins here don't like getting paged either, but ours certainly don't. And so after one page, they start getting cranky, but after continuous pages every few days for 2 months, they start getting really cranky, which naturally enough leads to fixing whatever the bug is. So before August, September, back in March, and this one was kind of my fault, we had some different problems. And this was just, you send a request in for, say, all the history for every single build operation or related anything that happened over the last 3 years within Red Hat, and that gets kind of a bit of data. And the way Koji works is it assembles a single XML RPC response, which is all XML, which isn't very succinct, and it will do all that in memory and then start sending it over the network, and that kind of runs out of memory. So that was back in, April or so, at which point the single process that was using too much memory would go into swap, Koji would lag, and would say, what's going on? They'd log into the server, couldn't actually log in because SSH was trying to load from swap, and that wasn't very pleasant. So that's when we set up the Nagios alerts for it, and we also use setRlimit, which says basically if this process gets too big, kill it, do a core dump if core dumps are enabled, and just get on with your life. And unlike the killer, that hits before it goes into swap, so you don't get any lag. And the other result from that was that we kind of lost our trust in Koji, and that, oh, okay, there's probably another bug in Koji that runs it out of memory. So that's naturally where we looked. If maybe someone else is doing a bunch of really big calls, or maybe there's some other bug because there's been a few other changes in it. So we had a bunch more logging. We run through the Apache logs, find out that some guys in Japan have been hitting it every few seconds and think maybe that's a problem, so we put a firewall rule in to block those. We talk to the kernel guys and see that they've got a monitoring script that does a whole bunch of queries every time they want to see where their kernel builds are up to, and so we encourage them to stop doing that. And of course, they've all been doing that for months, and that was nothing to do with the problem, so it doesn't fix it either. Okay, so maybe that's not the problem. Maybe there's a long-term memory leak. So we're using ModPython. ModPython in rel 5 is one of the older versions which doesn't actually give back all the memory when Python does its garbage collection, so maybe there's a leak there. What could we do to fix that? Well, we could upgrade to rel 6, which has had better performance for other things, but doing a major upgrade when we're already not sure what's going wrong isn't really happy. We could switch to WSGI and do all the management of it ourselves, but that's kind of a big code change, so that's not really a great idea either. What we actually did was reduce the max requests per child so that the Apache subprocessors just get killed once they've serviced about 200 requests. So kill a process, kernel reclaims all the memory, should be good. and that didn't help either. We also started having a look at doing kind of deeper Python debugging, but none of this really should matter because the setr limit's a kernel thing, and if the process gets too big, then it should be killed. So it shouldn't really be a matter of just one process. It should be a matter of a whole bunch of processes that are too big. So at that point, you're thinking, okay, the average memory usage per process times number of processes, if that gets more than your available memory, you hit swap, stuff starts going slow, you get more requests queued in, more processes get started, eventually you run out of memory and everything crashes. Okay, fair enough. So Apache has options to reduce the maximum number of clients you can have. So we put that in place, and in theory, that should help things, but it also means that you can't have as many simultaneous requests as you could before. So if your average process is running at 20 megabytes, I think ours were running at about 40 megabytes, you can have a whole bunch of those at once. Our maximum process size is a gigabyte. You can't have so many of those running at once. So there's a balance between limiting the maximum number of connections for a small average size and the maximum number for a large maximum process size. So we tried playing with that a little bit uncomfortable with it. Wrote a test script to fire off a bunch of connections from a single host to actually make Apache hit the limit and make sure it didn't crash for just really light usage with lots of simultaneous connections. Basic approach which seemed to work was just opening up a bunch of sockets, sending the first part of a hard-coded XML RPC request through. That's enough to trigger Apache to actually assign mod Python tasks to all the stuff. Sleep for a bit there so that they actually finish loading and it has time to run out of memory. Finish it off, get the responses back. You can tell if Apache decided to kill stuff or not because there'll be an error in the response. And so that got us to the point where you could run it until Apache was killing processes and the machine wouldn't die. All very well, but a few days later the machine dies again. So try giving it some more memory. We were short on VM space, but managed to find a different one, double the RAM size, and naturally it still crashes. So none of that worked. Try with first principles. When debugging things, a soft toy is always helpful. And if the soft toy happens to have a beer that you can steal from it afterwards, that's also helpful. So the idea of soft toy debugging is that you need someone to talk to, but that person doesn't have to be intelligent at all, and so you might as well not waste the time of someone intelligent, because you just need to explain things in really simple terms to yourself to find out what the problem is. So if you're running out of memory, how do you know that you're actually running out of memory? In this case, we know we're running out of memory because the killer is activated. The killer activates because the kernel doesn't think it's got enough memory. So how does the kernel track memory? It tracks memory according to what processes have allocated and what internal data structures it has. So we can track the memory usage by processes by saying, okay, we'll look through /proc or we'll look through top and just add up the RSS size. Kernel memory structures, if it goes there, there's a file in proc called, slabinfo, which tells you complicated stuff that you really have to know about. Okay, so we'll do that. And what we found out was that at this particular instance in time, we had about 4 or 5 gigabytes of memory used with about 20 or so Koji processors, each using about 50 meg of RAM. That adds up to about a gig, not about 4 or 5 gigs. So if it's not the processes, then what's the kernel doing? So have a look in proc slabinfo, and that was the next thing I saw on IRC. So we do a fair bit of stuff over NFS on that host. We populate a whole bunch of repositories, and every time someone uploads a new package, and we want to include that in the in the chroot that we're using to build the next set of packages from. We'll update a repository and fill out a tree for it. So if that thing's getting way too big and using up all of memory, that's not good. It should be getting cleared, but apparently it's not. So if that's the problem, it's a kernel bug. It's not a bug in Koji at all. Slightly worse if you're working at Red Hat, it's a regression in the released Enterprise Linux 5 kernel, which is not something that's meant to happen. So evidence for it being a kernel bug at that point is, okay, all the memory's gone to something in slab info. It's obviously the kernel that's allocating everything. And as it happens, all these crashes only started when we upgraded to RHEL 5.7. That was a Friday upgrade, started crashing on the Tuesday after and continued crashing every few days after that. Okay, that looks pretty suspicious. Evidence against was that all of the other RHEL 5.7 systems were working fine. And yeah, whoever trusts the developer when they blame something else as their problem rather than taking responsibility themselves, right? Sysadmins? No? So yeah, the result at that point was kind of a hung jury. The sysadmins thought it was our fault, we thought it was the kernel guy's fault. Kernel guys couldn't really comment because they didn't have enough data. But fortunately, unlike with real juries, we can just try the case again. So getting data for this sort of thing sounds easy enough. Just run a little shell snippet like that. I like doing everything on shell one line. It's probably not healthy, but hey, there you go. Yeah, that's expanded for demonstration purposes. Normally it would be a single line on the shell. And that works fine when the system's running normally, but when you start getting processes using up all the memory and everything goes into swap, during that sleep one, all the date free ps, cat, echo commands are getting swapped out. So when you get back to your next run, it takes a few minutes to actually load up date, takes a little bit longer to write it to a file, it then takes more time to load up free, and you get data right up until it starts crashing, but you don't actually get to see it crash. So that's not really helpful. So at least my solution to this was write a script in Python to do all that stuff internally. If you're doing stuff in Perl or in Python, presumably in Ruby, then all of that's in one binary. The script will get loaded and parsed when it's initially run, and as long as it just keeps in a loop, it'll stay in memory. If it's just opening files in /proc, there's nothing to get swapped out. And you can stay working and functioning right up until the machine gets rebooted, or the killer goes crazy and kills everything it can, or there's a kernel panic or whatever. So this was mostly just munging through files in /proc. And yeah, the only trick I did, which I'm not sure was even necessary, was I wasn't even game to sleep for 5 seconds in case my process got swapped out. So I just do a little for loop to sleep for 0.1 seconds instead. And that worked. That got me data right up until it was deep in swap and ready to be rebooted. Now, is that visible to anyone out of the front row? Yes? Excellent. Okay, so it's not actually visible to me, funnily enough. Yeah, so that's designed for a 1280 by 1024 or something display, or maybe 1600. I don't know, it was to fit as much stuff on the screen as possible, so I'd load it up in Firefox and scroll across and whatever else. What you're seeing there in the red line that goes down is available memory, including swap and cache. The blue line that goes up is the NFS inode cache usage, and the purple line just beneath it that also goes up is the dirty NFS inode cache, which we found out later was really the cause of the problem, which is why you can see it on the far right. going right up to the top. This data is from a test machine I was using to debug the problem, not the live system. Okay. Now, hopefully you can still hear me. Okay, so that point there was where I ran a separate script, which was just a Python thing that made a list as long as it could until it got killed. So the result at that point was that stuff wasn't getting freed. So you'd think if there's high memory pressure, then the kernel would clear out all these redundant NFS inode cache stuff so that the stupid Python process could fill up all of memory, then crash, instead of filling up half of memory, then crashing. Doing while true x, making x equals a list, while true x.append range 1000, x.extend range 1000 is a great way of using up memory really quickly. So what happened here was that I ran sync and then did the same thing. And the excellent thing is that sync somehow manages to tell the kernel to, okay, you're fine to release all these stupid NFS inode cache stuff that you don't actually need. So when we do memory pressure at that point, we get free memory again. The way we discovered that was we were doing all this graphing. I logged onto the box and didn't know what I was doing, so typed sync, as is my wont. And then went off to lunch and came back, and the sysadmins told me, hey, look, there's no problem. See, that's getting cleared. What? It's getting cleared? What happened? No one did anything, right? Okay, that's strange. Maybe I'm completely wrong. Look through my bash history and the sync commands. That's strange. So yes, pitches are very useful. They're very persuasive, allow people to see the truth behind whatever else. And it was the pitches like that we managed to pass through the kernel guys to actually get a fix. So yeah, our process for getting the real fix was to file a Bugzilla internally. Fortunately, our manager's kind of high up because he's the guy managing all the release processes for all of the Red Hat products, so he gets to ping someone and they respond pretty quickly. If you've got kernel problems and you don't have nice Red Hat or kernel people to poke with a stick, and you don't have paid people, I don't know what you do. So yeah, we got that fixed, and let's see, October or so, our updated kernel got through. It was excellent. And in the meantime, we could just, since we'd found out sync fixed everything, we had a cron job that ran sync every 5 minutes. The problem did not reoccur after that. So yeah, our only other issue was getting a test case, a reproducible test case, because OK set up a company that builds lots of products and have hundreds of developers all committing to it, and the production system, and then have it crash, and that's your reproducer, isn't really very useful. And at least as developers and non-kernel developers, we didn't know what the actual problem was, so our best solution was first copying huge trees of stuff around, which on shared NFS volumes, which is where we which is, well, the only sort of NFS volumes we had, causes problems when you don't actually make sure that you've got enough free inodes. And it takes a while to copy trees over NFS because you're first having to read the data, then write it out. So it was pretty easy to write a simulator for that, as in run find over an actual tree. That gives you the basic structure, gives you the size of the files, gives you which ones are files, which ones are symlinks, whatever else. Write up a basic Python script to dump out files in similar names with similar sizes and with similar sorts of symlinks. Turns out none of that was actually necessary because kernel guys know what they're actually doing. The test case that actually reproduced it is pretty much that one, as in touch a bunch of files in a directory and keep doing it forever, and eventually you'll get too many dirty NFS inodes and you'll run out of memory. As it turned out, the patch that was the problem was one of the upstream patches backported to RHEL 5.7. A problem actually exists or existed in the upstream kernel and RHEL 6 as well. The reason it didn't affect upstream and RHEL 6 people is because the NFS inode cache in those versions of the kernel is much, much smaller. It's about a kilobyte in RHEL 5. It's about 500, 300 bytes in RHEL 6 and upstream kernels. So you run out of memory much sooner in the earlier kernels, but you still can in the newer ones. And I had something else to say about that, but I don't know what it was. And so yeah, that was our success, and that's me out of time, so you're welcome to ask me questions over lunch, I guess. Yep. Okay, thank you very much.
Okay guys, we're off to lunch now. Just a quick announcement. If Sarah is around, can she please wander up and make herself known? Thank you.
Excellent.
Sweet.
The presenter's console is awesome.
What, yeah, so what's that?